All right, I think I got it. I think it's going to work. Let's find out. So, we know the noise of the system because we measured it, right? And we need that noise variance for the support, the constraint for the support. If you supply support and you supply a noise variance, this is all the data consistency stuff that we've been messing with. Right? We project outside of the support. So we need the noise variance that's still coming into this code. What about data consistency? Okay. If the A matrix was perfect, then yes, AX minus B, the L2 norm of AX minus B would be less than the noise variance times the number of elements. That would happen. But A is imperfect. So we need a bound. We need a reasonable bound on A. How do we get that? Well, we need to know what the L2 norm of AX minus B is, what the variance of AX minus B, which is sure based on the noise of B, but it seems much more based on A, right? ADC in particular. How bad is that, right? Well, we could come up with a metric for this. We could calculate this using the auto-calibration region. Actually, I don't think we need the auto-calibration. We could just calculate this, right? So let's see how that goes. I was tinkering around a little bit with it and I got something. So let's see what happens. Okay. So that's AX for the optimal image knot that minimizes AX, the L2 norm of AX minus B. Now let's compute that norm. What is GDC? Just the L2 norm of X minus B? Right. Okay, let's compute minus B 32 divided by NB. So here was me doing the similar thing with the auto-calibration region. Oh. Wait, that's right. Okay. So GDC minus B is 32, but temp divided, this is divided by, okay, so what is GDC divided by NB? 2.2 times 10 to the negative 4. Temp is 8 times 10 to the negative 6. Huh. Here is much higher. Okay. So temp is 8 times 10 to the negative 6. This value is 2.6 times 10 to the negative 4. So the values outside the ACR are wronger than the values inside. That makes sense because the sensitivity maps are probably better in their lower frequencies than they are in their higher frequencies, right? Okay. That's going to be the bound. This image not. Where is it? It's there. Where did it go? Where did it go? Where did it go? Where did it go? Oh, goodness. Okay. Air bound is equal to that. Huh. We're dividing by NB and multiplying by NB. And there's no reason to believe that this is Gaussian. Okay. Where does image not get created? $112. GDC happens down here. Call this image LSQR. Now, I would have, I think I would have thought that we could warm start with LSQR and it would get us farther faster. What just happened? I think we need, oh, because I didn't reshape. Would that work? Did that work? Looks like it did. So now let's come on down to compressed sensing. Is the problem still infeasible? I'll bet you it's not. This value. Oh. For this, we also need LSQR. Okay. Now I can finally see if it's feasible. That value, non-singleton dimensions of 2 input arrays. What's going on here? What? I thought I already reshaped it. Did I not? Hey, Protost! Protost is back. Protost, we may have just found the bug. That's 0.13. What's the indicator? That's 32. Okay. So this problem is feasible. Protost, we have found a feasible problem. And we are going to see now what the result is. We haven't had a feasible problem in a long time, Protost. Yes, feasible. Bigger. I'm going to show scale, absolute image 5. That's still terrible. That just can't be. That just can't be. The problem's at least feasible. But for some reason, compressed sensing is doing nothing at all. This can't be. we needed a much higher bound. I gave it a much higher bound. We must be using noise var somewhere that I don't think I forgot we were using. Right, in the proximal operator. Okay. Okay. We've got a bug. We have a feasible problem, Protoss, but we have a bug. So the thing that we're minimizing less than or equal to is, well, it's that bound. So that's x minus b. The L2 norm of x minus b is less than or equal to 2 times the square root. No, sorry, the square root of 2 times the bound. So the bound is actually we've gone through some major learning, Protost. We've done some major learning. The big lesson that we've learned, Protost, is if you need an error, you might want to measure it. Okay. This if statement is no longer relevant. We're still using this. Noise var. Oh, it's this rad that we're calling this. Okay. So we don't need that. This rad is the radius of the ball that we are projecting onto. Will that work? No, it clearly will not. I think that thing called bound is going to be the error. Right, GDC, right? Oh, we do need the bound. Oh my goodness. With that definition of the bound, is it possible for this thing to be infeasible? I don't even think it's possible for this thing to be infeasible anymore. This is absolutely amazing. What did we call it before? Bound GDC indicator. I don't know whether to call it bound GDC indicator or GDC error. I guess we'll do it like that. Think it'll crash again? I do. It's running. Whoa, times 10 to the 22. That's not good. And that's even worse. Okay, I've definitely broken something now. Biggest issue is that the code's so bloody complicated. Why did tau go up so high? Oh, because the objective value is 0. Is our bound too high? It is. Just to check. Let's not get excited or anything. Okay, if we're using the ACR, and the indicator function, the GDC error is going to be the ACR error times NB. Tau is still going up real high. Yep, times 10 to 25, which means that, okay, that can't be. That's just impossible. Why do I say it's impossible? I'll show you. Oh boy. I'm gonna have to revert. .13 and this 0.6. Okay, so it's feasible. And there's a bug, rad. I'm going to revert. That's what I'm going to do. Okay. Now, if I do compressed sensing reconstruction, with noise, so noise var times 1d5, right? What is this value? 0.8. I think this is going to give me a good result. That is an excellent result. That's a good result. I guess not excellent, but good. Very good. Okay. Where is this bound? Okay. This bound was being created that way. Now we're going to solve the problem with LSQR using only the data we collected. Okay, so we've done least squares reconstruction. Now we're going to find GDC, apply MFS to image LSQR minus B. GDC error, like error, GDC is equal to that. We're going to divide that by num NB. And if that's the case, then we want the indicator function we want GDC, the result of GDC to be less than that bound. We may get rid of this times MB, divide by MB in a second, but we're not doing it right now in case we need to use the ACR. Okay. Then what's the radius? Right? So this is the radius. That's going to be the value that gets used there. So now my question is, what is that radius value? 3,000. Well, that's too high. Now let's do it for the ACR. ACR mask. That's right. And maybe the error increases dramatically when we use all of the k-space data collected because the signal-to-noise ratio of the outer k-space values is less. The noise is the same, but the signal goes down. So maybe we should really only be using the ACR to find this bound. Okay. Apply FS image LSQR. FS image LSQR is equal to that. Mask ACR mask. Well, mask ACR FS image LSQR is equal to FS image LSQR ACR mask equal to 1. Norm that minus ACR squared divided by sum ACR divided by num ACR. ACR error is equal to this. So make it the same. So I could just use the 2 here. I'll put a 0.5 there. Oh, we don't want times NB because we're multiplying by NB there. Oh, wait a second. This is a problem. Did I have a bug? Was that the issue? Okay. What's the radius now? 3,000? That's the same value. How did that happen? I guess I divided and multiplied by enough NBs that everything canceled out. Okay, so this should have been divided by NB. Now what is it? 8. 8, you say. How's that going to perform, do you think? Tau is reasonable. That is terrible. Let's make sure the proximal operator is correct before we freak out too bad. Well, the radius, 0.8 for good result. So I'm off by 10. I'm off by 10 and the answer is bad. Eight. Let's just make sure there's still a good result with 0.8. Point 0.8, the result is good. 0.8, 8, the result is bad. Okay. Going back to this ACR stuff. What's the radius now? $1.6. Now, I suspect this will work, but the question is, does this work? Or did I just hand tailor an algorithm to the one data set I've been looking at? I thought it would work. Is that actually better than zero filled? Disappeared. Yeah, it is. It's better than zero filled. Still got this grid pattern there. That's maybe what we got. Okay. Just so I know, what's the answer if I pretend that the ACR was size 7 by 7? No, it's 2. Huh. This is the estimate of the variance. I shouldn't have changed it. Yeah, it didn't. Okay. How hard is it going to be to change this data set? Is that it? This is also an ankle. And of course, the noise coordinates are not correct. How is that also an ankle? What is 7? Brain. Okay. Let's try brain. .1 is the radius now. Tau is behaving reasonably. That looks bad. What was that value? Oh, that value for the other one was 8. What is the radius now? 5. So about 5 times larger. That's significantly worse. You need it smaller, not larger. Oh, but what was the ACR over there? 19 by 19. Yeah, that's right. I see a factor of 2. This is GDC. Yeah. So if that was the four. There's an error here. We do need a 0.5. That's pretty bad. My goodness. I need to leave. I'd like to fix this. So we did need a 0.5 there. Why? Because the bound is for GDC, and GDC has a 0.5 in it. So it's not quite right. We don't want a 0.5 there. We want the 0.5 there. I guess, which is the same thing, of course. Yeah, I think that's right. Point 0.8. How many times have I struggled with this 0.5 from GDC? That's bad. What's the sample fraction? 0.3. It shouldn't be bad. It should be good. This also shouldn't be hard. Like, we should be able to just measure the error. It doesn't matter. It shouldn't matter. I don't understand why it matters whether we use the... Okay. I think the thing to do is use a weighted norm. We're going to leave that for tomorrow. We want to weight the norm with the magnitude of the Fourier values. If the values are high, then we weight the norm with those. We count those a lot in the norm. And if the values are low, then we don't. This doesn't have weighted norms. Okay. Weight is easy. Maybe. I don't know how to do it in such a way that, like, divided by the sum of the square root of ACR. I want the weights to add to 1. So this is a weighted average. Okay? So we just did the thing we were going to do tomorrow. It's hard to stop. Incompatible sizes. Ah. So is that it? It's bugging me to work with the brain and have to load the data all the time. What's the radius? 6 times 10 to the negative 4. Something went terribly wrong there, didn't it? One compressed sensing problem is infeasible. Okay, the thing is that we're taking the expected value. Variance is just the expected value of each value minus the mean. With noise, the mean value should be 0. So now we're just taking the expected value of the value squared. Oh, right, so this is not noise. The true values are here. So the mean are like the true values, the ACR values. The ACR values have noise in it, but it's tiny compared to the errors from the system simulation. The sum of the norm weights should be 1. And it is. Ah. That's at least an issue. Five times 10 to the negative 4. This is now a weighted average. Ooh. Oh, it's the sum of these weights squared that should be 1. One times 10 to the negative 3. Problem's infeasible. So we're going to take these values take their magnitude, square it, add a whole bunch of them together. That's the expected value of the variance. Or after dividing by the number of elements. That's the right answer, which is the old answer. And that's now something times 10 to the negative 2. Is that infeasible? Yes. That is still infeasible. Oh, did I just enter a bug? Take their magnitude, square it, oh. So these are the norm weights. That should look a whole lot like the ACR, and it does. Are they different? No, they're the same, and that makes total sense. Take the sum of the weights times the elements divided by the sum of the weights. And the sum of the weights is 1. You just take the sum of the weights times the elements. Here I made the sum of the weights 1. Arithmetic mean. So we shouldn't be taking the mean here? Is that what you're telling me? It doesn't make sense. Oh, I need to take the sum of this. $508. 22. I feel like I'm shooting in the dark. If we have three values, 1, 1, 1, what's their average? 1. Let's take the weighted average. So we're going to weight the first by a quarter, the second by a half, and the third by a quarter. Well, by multiplying by ones, it's all the same. Hey, Protoss, what on earth is a weighted average? I want a weighted variance. That's the mean. Oh, V1 is the sum of the weights and V2 is the sum of the weights squared. Well, that's clearly different than what I was thinking. All right, let's do that. var error ACR is equal to we're going to call V1 is equal to sum of the norm weights. That should be 1, right? So it's just going to be 1. V2 is equal to sum of the norm weights squared. V1 divided by V1 squared minus V2 times the sum of what? The weights times the value minus the mean squared. Norm weights times the values minus the mean squared. All right. What is that? (2.6 times 10 to the negative 5. Norm weights? No, those are. What's the problem? ACR error is undefined. Okay. (1.4). That gives us a decent image, doesn't it? That's a decent image. Okay. Now let's do the brain. That's very good. Oh, that's truth. Of course it's very good. Okay. That's bad. That's real, real bad. Hmm. No. Okay. With that, gonna let it stew again and see what we can figure out. Stream again tomorrow. See you guys later.